probably know if you have seen our website. The first one was in 2006, the second one in 2010. So this is partly supported by the EU FP7 program, the Inter-UK programs, and so on. Gautam, I'm sure, would tell the details of the various agencies which have been kind enough to support us. So the idea of the workshop is that it's going to give a pedagogical tour of the current exciting areas on how to model infectious diseases. And we've got leading experts from India as well as abroad who are going to give a series of lectures as well as computer lab sessions in the next 6 days, which is going to be followed by a 3-day conference where Indian and international experts are going to talk about their research problems. Okay, so a few organizational details. So we have a few volunteers here who are going to help you with any queries you might have. So I might ask the volunteers to kind of just, as I say your names, to kind of just raise your hands. So there's Tonmoy. Tonmoy, just raise your hand. Yeah, thanks. There's Dr. Anupama, Reshma, and Ria. Okay, so if you have any questions, and of course Chandrasekhar. So if you have any questions, you could just ask them, and they would point you out the solution and so on. All right, so we have here my colleague Gautam, who is a co-organizer of this meeting. So Gautam is going to also welcome you to the workshop and conference, and also tell you something about the schedule and lab sessions.
Okay, hello everyone, I'm Gautam Menon, that was Shitabra Sinha. We apologize for the rain insofar as you can assign any responsibility for it to both of us. And this is actually a small but pretty campus, and it's not looking particularly pretty at the moment because it's all wet and various leaves have fallen down. But we hope there won't be any serious disruption to the program because of the rain, and we're very glad that so many of you got here in time. The program, the latest version of the program is available at the desk outside, but as with all of these things, the program is a little bit dynamic, which can change from day to day. So look at the program on that particular day, and we'll try and update it on the website. You should have information by now about how to access our wireless, for those of you who have laptops or other devices with you that can access wireless. We have computer labs, and Sebastin, Gwen, and Anton are an integral part of running those labs together with their lectures. The labs will be held one floor up from here. So you go out, go up the stairs, and turn to your right. That's our computer center. And the labs will be held there starting tomorrow from 9:30 to 11:30. So that's the first lab. There are 3 lab sessions in all, each of 2 hours. And presumably some of the other speakers may also have lab sessions. Security, in general, don't leave expensive sort of purses, expensive computers, expensive mobile phones, etc. over here. In a spirit of abundant caution. It's not necessary that things will vanish, but we would rather not you be the test case where that actually happens. Food, as Shitabra says, is on the other side of the campus. It's just a short walk. Look for the volunteers to take you there. This is a campus where you can pretty much walk around. There are nice places to sit. So this is one place you can certainly sit till they close it up at 6:30 or 7 in the evening. There's also on the 4th floor, the topmost floor, right at that end, there is a large lounge, which is our coffee lounge, where you can sit and access wireless and so on. There is also a room just below that, which is a somewhat smaller room. So in the gaps in between, especially in the evening between about 5:30 and 7:30 when dinner is served, that's when you might want to sort of wander around a little bit, go to our library, etc., which is just the building here. We're a small campus, but we're a very accessible campus. Feel free to walk around, talk to people who you might meet. And is there anything more? That's about it. Let me invite Sebastin to come and give the first lecture.
Should I use this? Okay. Okay, so good morning, everybody. Can people hear me well? Can people hear me in the back? If someone hears me in the back, can you wave at me? Yes, someone waves at me. Okay, great. Okay, so the idea for this course is, yeah, it does not work. would you rather I use this or I speak into? I'm happy to speak into this. Okay. So the idea for this course is to give you an introduction into infectious disease modeling, and I'm not entirely sure what everyone's background is and how much of you know something about this maybe already. In fact, can I just ask you by show of hands, who of you has learned something already about infectious disease modeling? Okay, a few. Okay, so 4, 5, 6 people, yeah. And or who of you has ever used an infectious disease model? Okay, 1, 2, maybe, yeah. Okay, and then as a last question, because we'll be running some practical sessions, can I ask you, who of you has ever used a software called R? Okay, a few of you. Okay, well, I think this sort of reflects what we thought, because we realized that you have a variety of backgrounds. So what we'll do is we'll start from zero, really, and we'll start from the very beginning. So if you don't know anything about infectious disease modeling, if you have never heard about this, then hopefully that'll allow you to follow and to get something out of the course. But then also we'll progress to some more advanced topics that we're planning for the last day on model fitting and inference, which perhaps those of you that already have some experience with infectious disease modeling perhaps will also be able to get something out of and learn something new. And we'll have several practical sessions, lab sessions, where you can apply the things that you've heard in the lectures. And these will be done using R. But again, by the same principle, we'll be starting from zero. We're assuming that you don't know anything about how to use R, so we'll give you a bit of an introduction tomorrow on how to use R, and so hopefully you can pick it up from there. And just to go back, I should say, so it's 3 of us. So myself, I'm Sebastin Funk, and then there's Gwen Knight, who's sitting over there, and Anton Camacho, who's joining us tomorrow. We are all from the London School of Hygiene and Tropical Medicine. Well, Gwen has recently left and is now at Imperial College, but is sort of still part of the London School of Hygiene and Tropical Medicine. It's particularly nice to be here and experience some actual tropical weather, which we never have in London. And we left at it was about 4 degrees when we left London 2 days ago, so it's very nice to have a bit nicer temperatures here. And we're there at the Center for Mathematical Modeling of Infectious Diseases, where it's a group of us who all work on infectious disease modeling. Okay, so again, the plan is, so today I will give you an introduction, and then tomorrow we'll have a lab session, and we'll then we have more lectures on stochastic models and some applications in the coming days. And however, to start with, and it's always nice to start the day, it's early in the morning, start the day with a bit of activity, we'll run a little experiment. And what we'll do is we'll simulate an epidemic in this classroom. And the way this epidemic will work is it'll be an epidemic of the standing disease. Okay, so if you're infected, you will be standing. Most of you are sitting. I see there might be some people infected already, myself as well. But so the idea is that if you stand, you are infected. Okay, and the way this is going to work is if you become infected, yeah, and I will tell you in a second how you become infected. You will point at 2 people, and those 2 people then become infected. Okay. Let's see if we can work this out. So you become infected, you stand up, and you point at 2 people, and then these people have to stand up, point at 2 people, and so on and so forth. Okay, so I'll make a start. And so it's a bit of a big lecture theater, not entirely clear. If you think you're pointed at, then get up. Okay, yeah. Okay. Oh, yeah. Okay. We have a raging epidemic, I see. Yeah. Keep pointing. Keep going. All right, I think most people got infected now. We have some survivors. Okay, thank you very much. You can sit down again. Okay, great. Thanks very much. That was really good. So, okay, so in some ways that was a bit like an epidemic unfolds. Do you think was this a realistic description of how an epidemic will spread? What do you think? Yeah? No? Okay. Why not?
Because either it should be spatially related or you should know them so that you might interact with them. But here they point out people who are like well separated as well as people who they are not like.
Right. Okay, so that's a good point. So this was about, here you pointed at people that you wouldn't perhaps usually meet in daily life, so it's not like people of your family or something like this. Although perhaps there could be something that spreads in a classroom or something like this, but it's a good point. Okay, any other comments? Yeah? Right, that's right. So it could be more than two. You have only two hands and you only pick the two. That's very good, yes. Any other ideas for why this might be unrealistic or realistic? Anyone else has an idea? So what about the way this disease spreads, and that you stand up and then you point at two people? Is that how about this bit? Is that sort of realistic idea of how an infection spreads? Yeah.
Horizontal transmission.
Say again, sorry.
Horizontal transmission.
Horizontal transmission, yeah. So you would call that horizontal transmission. So do you think that's a realistic description of what's going on?
So actually, it is being propagated into like that.
Right. Okay. And there was another, yeah. Very good point. Okay. Yeah, we don't know the immunity. There's also other things. I mean, the fact that there's also you wouldn't necessarily choose people to be infected and point at them, and also you would only point at people who are still sitting. So what this means is you're choosing people who haven't been infected and then you infect them. That's not normally what happens. It's more that you encounter people perhaps randomly, and then they might, if they're not immune, then they might become infected. But here it's this kind of you make a choice, and in real life perhaps encounters are more chance. Okay, so we said that everybody infected two people, and in fact this idea of thinking about how many people everybody infects is an important idea in infectious disease epidemiology, and it's what is called the reproduction number. And the reproduction number is simply that, is the number of secondary cases that an infectious person generates. So in this case, in our simulation here, we said this is always two. Everybody infects two people. In real life, of course, people infect a different number of people. Some infect more, some infect less, and so on and so forth. So what do you think the number of people, if you think of this reproduction number, now think about a real-life epidemic or an infectious disease, what do you think this will depend on? How many people everybody infects? If you think of different diseases or different people, what do you think are the kind of parameters that go into what this number is? Yeah.
Basically, I mean, mode of infection. If they happen to be like, if there's a particular disease which spreads, if two people come, let's say 5-meter radius, then it has a higher chance than something. If you only share, let's say, it spreads through like saliva or something, then the odds are even lower, because that chance of that happening is much lower than you being in a 5-meter radius. So it depends on the mode of infection.
Right, okay, so it depends on the mode of transmission, right? This is really important. So for something could spread perhaps in a very efficient way, and so this number will be higher, or if something spreads less efficient, then it needs longer, and it depends on whether it's sexual transmission or airborne transmission or something like this. Yeah, very good point. Anyone else has any ideas for what this number will depend on? Yeah?
Where I am located, if I'm located in a very densely populated place or something, it's transmission.
Right, very good. If you're in a densely populated place, you will come in contact with more people. Yeah, so you can think about it. It depends on the number of people that you contact, and that will depend on your location and where you are located, and so on and so forth. Okay. So these are very good points. One way to break it down would be to think about that it depends on the number of contacts. So that comes back to this idea of population density, and also mode of transmission plays a role in there. It depends on then, if you do come in contact with someone, the probability of transmission. So that's how efficiently an infection transmits, how fast something can spread, how good. So if something could be very transmissive and everybody that you come close to can become infected, or something can be a very poor transmitter. So for example, measles we know is an infection that is very infectious. So you come close to someone and you're very likely to transmit the infection if that person is not immune. Whereas, for example, for something like Ebola, we know that you need some very close contact for a prolonged period, or you care for someone, you need to touch someone in order to get infected. So this probability is different. And then it will also depend on the duration of infectiousness. So if you're infected for a long time, I'll get back to you in a second. If you're infected for a long time, then you have a chance to infect more people than if your infectious period is very short. Okay, there was a question, yeah?
What's the degree of infection? Won't that matter? Because if the person is not infected to that level, isn't that also happening?
So the degree of infection, right, that matters, and and that can change from person to person, also over the course of an infection, right?
Some person is not that infected, so he cannot transmit.
Right. So there could be. Is what you're saying? There could be difference between people, whether someone is more infectious or less, depending on how ill they become or something. Yeah, exactly. That's a very good point. Yeah. So this is. I guess this comes back to the probability of transmission. So it's not. It's right. It's not only a function of which disease it is, but it might be that it depends on the person, or there might be variation between people, and also it might depend on where you are in the infection. So, for example, with HIV, we know that if people who become infected with HIV are very infectious in the beginning for a short period, for a few weeks, but then are less infectious for the time afterwards. And similarly, for example, with Ebola, people are the most infectious just when they're about to die, or even after death. So there's transmission in funerals and so on and so forth. So it can change over the course of an illness. And then the last one, again, was mentioned earlier, is it depends on whether people are immune. So it depends on the proportion of your contacts that are susceptible, because you can only infect those that are not immune, or in other words, that are susceptible. Okay, so we as a simple model, we could write this reproduction number for each person as simply the product of these things. So it's a number of contacts times the probability of transmission for each of these contacts times how long you are infected times the proportion of the contacts that are susceptible. So that could give you that number, the number of people that get infected. Okay. There's an important concept in epidemiology, which is a generalization of this reproduction number. So we said the reproduction number is different for every person in an epidemic, and it's different for every disease. And the basic, what we call the basic reproduction number, or R0, so it's this this thing here at the top, we call this R0. I don't know if this pointer works. Yes, it does. Okay, so R0 is, so we said we have this reproduction number, it can be different for everybody, and this R0 is the reproduction number under a very particular circumstance, and then it's an average. Okay, so the particular circumstance is it's the reproduction number in a population where everybody is susceptible. So everybody could get infected. So this is, think of something, you have a population and you have some new disease coming in where nobody has ever been exposed, there's no immunity or anything. Okay, so everybody is susceptible, and then you have the first infected case, and you think about how many people does that first person infect. Okay, what is the reproduction number of that first person? And you think of this in some kind of general way, so there could still be some variation in who that first person is, and there's some chance in how many people do you infect. And what this basic reproduction number, or R0, is the average of that. Okay, so it's the average number of secondary infectious cases that you get if you get a single infected case in a totally susceptible population. So it's a good indicator of what happens in the beginning of an epidemic. So you have this average number, and in the beginning you start with an infectious case, and then you have this average. So you know on average in the beginning, whilst the population is largely susceptible, how many secondary cases everybody will infect. And that's important because that tells you whether you can have an epidemic or not. Because if that number is greater than 1, if everybody infects, sorry, that's on the right here. If R0 is greater than 1, if everybody infects more than one person, so as we just had it in our standing epidemic, everybody was infecting 2 people, then you have this sort of chain reaction and some exponential growth, and more people get infected. Whereas if, on average, everybody infects less than one, so it could be, for example, a half. Yeah. So remember, this is an average. So if every other person infects one person, then this would be 0.5. So like this scenario here. So out of 2 people, you always get 1 new infection. Then you won't get an epidemic, and the number of cases will decrease over time, and it will die out. Okay. So this is an important concept in terms of whether you have an epidemic or not. And now, remember again, this is an average. So this is nothing anymore that depends on the individual person or that varies from individual to individual, but it's an average, so it's something that can describe, say, a disease. We talk about the R0 of measles or of flu or of HIV or something, okay? So if you think about, let's have as a little puzzle, think about 4 infectious diseases here. So you have measles, Ebola, malaria, and HIV. So if you think about which of this has the highest, or think of how you would arrange these in order of R0. So from highest R0 to lowest. Okay, so what would you say? Yeah? Which one do you think has the highest R0? Ebola? Yeah, okay. Ebola, does everyone agree with Ebola? Has the highest R0? Any other guesses? Malaria, okay. Measles, okay. Well, it's a wide range. Which one do you think has the lowest? HIV, yeah. Everybody thinks HIV? Okay. So obviously we have a range there, but normally, so malaria was a very good point. And the point here is that someone who has malaria could be bitten by a lot of mosquitoes and thereby infect a lot of others. And in fact, so in malaria endemic areas, R0 has been estimated to be up to 100. So one person could infect 100 other people on average in malaria. Measles, very good guess, is the most infectious airborne infection that we know. So it's very, very infectious. And in fact, it's now, of course, there's measles vaccination, so not so many people get measles anymore. But back before vaccination, in a country like, for example, the UK, by the age of 5, everybody would have had measles. Okay, because it's so infectious that after birth, very soon after you get born, you will at some point get measles and then become infected. HIV, again, depends very much on the setting, but it's been estimated to be between 2 and 12, depending on where you are. And then Ebola actually has a relatively low R0 with 1.5 to 2.5. And I said earlier, it doesn't transmit very, very efficiently. What that tells you, of course, is that this R0 value doesn't tell you how necessarily how dangerous something is or how deadly something is. And it also doesn't tell you how fast something spreads. Okay, so this could be it just tells you how many secondary cases someone generates, how many other people someone infects who is a newly infected in a population. But this could be over a very, very long time span. So, for example, measles, the time span of measles, you become infected, you're infected for about a week, then you become infectious for another week, and so it's about a 2-week span, your total infected period of being infected. Whereas for HIV, you can be infected for years, and you can transmit to others for years. So it doesn't tell you how fast something spreads, it doesn't tell you how many people necessarily die. But it tells you whether something can cause an epidemic or not. And the potential of malaria or measles to cause an epidemic is much higher than the potential for Ebola. So in theory, Ebola is easier to control than either of these. But of course, once you get Ebola, it's much more deadly, and also at the moment, we don't have a vaccine. Well, we might have a vaccine actually now, but as of 6 months ago, we didn't have a vaccine, whereas for measles, there's a very efficient vaccine. And this concept of the basic reproduction number, in fact, has also been popularized. I don't know if you can see this, but and I don't know how many of you have seen Contagion, but this is Kate Winslet at a board explaining the basic reproduction number for flu, smallpox, and polio in this deadly outbreak of flu to people at the Centers for Disease Control in the US. And the point here being that this is something that is actually, it's a very intuitive concept and something that's also being used in in public health decision making and in policy making. Okay, and there's a list here. I don't know how well you can see this, but this is measured values of R0 in different settings and for different diseases. So you have here measles in different places, so from England, Wales, US, Canada, and so on. So it's 13, 14 here, 15 to 18, and then 5 to 6. So you see there's quite a lot of variation in here. There's different time periods as well. And then pertussis or whooping cough, chickenpox. And perhaps just to point out to you, so that down here is HIV, and I said it's 2 to 12, so it's been estimated to be 2 to 5 in England and Wales between male homosexuals, and then it's been different in, say, in Uganda in heterosexuals. So the important thing here to realize is you can actually get quite different values of R0 even for the same disease. And the value you get depends very much on the context. So even though it's now an average, and we're saying we're averaging over everybody, so we don't have this individual variation anymore, we still have a lot of variation depending on things like the population density of any particular population, contact patterns, host factors, so things about immunity and the immune system. It could be things like seasonality, of course, and control measures, and other things that affect what the exact value of R0 is. Okay, so we've been talking about this R0, but the value of R0 doesn't necessarily tell you what will happen to any particular outbreak if you're at the beginning of an outbreak in the future. It doesn't necessarily help you explain the behavior of an infectious disease in a population over time. And this is where we get into infectious disease models and modeling. And this is what we'll do for the rest of the course, but we'll keep coming back to this reproduction number, so it's an important concept to grasp at the beginning. Does anyone have a question about this basic reproduction number? Does this make sense? Does it make sense to you what this number represents and what the point of it is so far? We'll come back to it and what the point of it is. But are there any questions at this point? Okay, no questions. Great. So, which means we can move on to mathematical models and infectious disease models. And so, thinking about what we mean by a mathematical model is, there's a definition here from the Oxford English Dictionary, in that it's a simplified description, and in fact the dictionary mentions even already mathematical, but a model can be many things, and you can think of model railways or models of a built model of a building or something. So it's some kind of simplified description of a system. And in the case of an infectious disease model, what we usually talk about is we have a set of equations that describe how something spreads in a population. So for example, we might want to describe the standing epidemic in this classroom and think about what are the properties of this, how can we describe this, can we generalize this, if there's a standing epidemic elsewhere, can we predict what will happen there depending on what we know about the population, and so on and so forth. So we have some equations that describe the spread of something in a population, and importantly, we attempt to capture key processes and ignore unnecessary detail. So you might get away with a very simple model, because if it captures all the important things that you want to talk about, you could have a very simple model that ignores a lot of the real properties of infectious disease spread, just like this little train here ignores a lot of the properties of a real railway, and it won't get you from Chennai to Bangalore. But it might be that what you want to study about your system is completely described by your model that you are looking at. And you can have models of increasing complexity, but if the simple model is enough to understand what you're looking at, then perhaps you're better off with a simple model that you can understand and describe very well, and it doesn't take so long to build. And the reason we do this, and the reason we use infectious disease models, is, I think, can be grouped in these three categories. And the first one is understanding. So you want to understand transmission dynamics. So by dynamics, what we mean is we want to understand how something behaves over time and how it perhaps changes over time. So we want to be able to understand, for example, if we look at the last 10 years of, say, measles transmission in India, perhaps we want to understand why something is increasing or decreasing or staying the way it is, and understand the patterns behind it. Perhaps we want to understand who the risk groups are, where there are so-called hotspots, so thinking about geography, so thinking about whether there are certain areas that are particularly affected, and also understand why these are particularly infected. And this is the point of this is then to highlight gaps in knowledge, and also often to inform what kind of data we would need in order to perhaps understand better what's going on. And so that's the first bit, is about understanding. The second then, which is intricately linked to understanding, is about assessing control strategies. So for example, think about a situation where you have a limited vaccine supply and you want to know how it should be distributed. Which populations should you target? Where should you? And of course, as I said, this understanding will then help you to target different groups. But with a model, you can actually test. If you have a good model that describes how your infectious disease spreads, you can then test some intervention. You can put some interventions and some or control strategies into the model and see how well they do at reducing infection or coming to an outcome that you're after. Think about stuff like travel restrictions and school closures. And then lastly, and again, this is linked to the other two, you might want to predict what will happen in the future with your disease. Okay? That's not always what you want to do with a model, and it has to be done very carefully, because often it's notoriously difficult to tell what will happen in the future if you don't know all the parameters that are involved. But you might want to know things like how many cases do we expect of something in the next week, or are we approaching the peak of an outbreak, and or things like more broader things, more general things. What is the impact of a changing climate, perhaps? So what if temperatures increase somewhere? Will you have more mosquitoes? Will mosquitoes lead to more malaria? And so on and so forth. So generally, it's grouped into, I think you can group it into these three things. Okay, and there's a quote which is attributed to various people, but most often attributed to a statistician called George Box, which is that all models are wrong and some are useful. And the important thing is that we want to come up with models that are useful, because a model is always wrong in the sense that it's never a complete description of your system in the real world. It's never a complete description of your epidemic. It will always be a reduction, a limited reduction under some assumptions. So you make some assumptions. You say, okay, well, I'm only looking at these couple of variables and these couple of parameters, and I think that's enough to describe what's going on. And then the important thing is whether that can be useful and practical. Okay, and so let's get into what these models actually look like and what you can do with them. So this leads us to compartmental models. And what you do with a compartmental model is you look at your population and you divide it into certain, what we call compartments, or perhaps categories, you could say, groups. And the groups depend on your status with respect to the infection. Okay? So for example, thinking back of perhaps the simplest compartmental model, and in fact a model that I think is a good description of the standing epidemic that we had earlier, is the SI model. So you have two groups. You have susceptibles and you have people who are infectious. Okay? And we call this S and I, these are the compartments. And we also sometimes call them state variables. And what we mean by this, so they are variable, it means they change over time. So we could think of the standing epidemic, everybody who's sitting is susceptible, everybody who's standing is infectious, and the number of people who are sitting and standing was changing over time, and this is what we describe by S and I. Okay? So it's number of susceptibles, or number of people sitting in the standing epidemic, number of people infectious. Okay. And you have this population size. You have N is simply the number of people who are susceptible plus the number of people who are infectious, which is the population size. And this does not change. So again, can think of earlier, everybody was either sitting or standing, but the total number of people didn't change unless someone got tired and left the room or something, which I didn't pay attention to. But importantly, so we call this thing a parameter. So what we mean by a parameter usually is something that doesn't change. And we'll be using these words a lot, so I just want to introduce them here. So if something's a parameter, it means it doesn't change. If something is a variable, it means it does change. Okay. And then we have this thing here. So you see this arrow, and then we have this Greek letter here, lambda. And if you're wondering why we use this and funny Greek letters in infectious disease modeling, I don't know, but for some reason it's what we do. So I'll do it as well. This one's called lambda, and it's what connects, what makes people who are susceptible infectious, And what we call this, what this is in the SI model is something we call the force of infection. And the force of infection is the probability per time. So you choose your time. The unit could be a day, week, month, or a year or something. Probability per time that someone who is susceptible becomes infected. Okay, or perhaps in the standing epidemic, perhaps you would think of it as a probability per second. So every second, what's your probability of getting infected? Okay, and if you try to break this down and think about what this probability is, you can. The way we usually break it down and the way you can think about this is and again it comes back to what I showed you earlier with the reproduction number. So it's the number of contacts per time times the probability of transmission for each of these contacts times the probability that the contact is with someone infectious. Okay, so you are someone susceptible, and you want, for the force of infection, you want to know what is my probability per time of getting infected. That's simply number of people that I contact in that time times the probability that they infect me times the probability that they can infect me if they are infectious times the probability that they are infectious. Okay, so we can write this. So for this lambda, we can write c times p times I over n, and this c times p we often call it beta, which is the infection rate. So for the force of infection, we write beta times I divided by n. Okay, so beta is a parameter. It doesn't change normally. Okay, and then so we said that I over n is the probability that a contact is infectious. So what we mean by this, so n is the population size, and I is the number of people who are infected. So you can think, okay, so the probability that someone who you meet is infected is simply 1 divided by the other. Is the proportion of people that are infectious at the moment. If half the population is infectious, then the probability for any given person that I meet that they are infectious is 1/2. Okay, but so that implies that everybody that this half, that everybody has the same probability of getting and having an infectious contact with everybody else. Okay, because we're just saying, okay, we take the whole population, number of people infected divided by number of people, divided by the population size, and we say that is the probability that anyone I meet is infectious. Okay, and this is what this is often called is the principle of mass action, which is from a term from chemistry, because it's the whole population that sort of exerts this infection pressure on you. Now, is this realistic? Question to you. Is it realistic? Who thinks it's realistic? Show of hands. Who thinks it's not realistic? Show of hands. Who doesn't care? Everybody else. Okay, so of course not realistic, and you can think of in many cases where who you meet will depend on context, and you don't have the same probability of coming in contact with everybody else. So if you think of influenza, then perhaps it's someone who's in your school or in your workplace or in your family that you get infected by, and it's, of course, especially for a sexually transmitted infection like HIV is not realistic, and so on and so forth. But, and this comes back to the quote I showed you earlier, sometimes it's still a useful description of the system, and sometimes it's still a good model. Okay, so it comes back to the question of, do we have to be completely realistic in order to have a good model? No, of course not. Okay, so then we make a decision of which bits of realism we don't need, and then sometimes, and it's important to make the distinction and to realize when it is a good model and when not, but sometimes when we describe an infection in a population, we can get away with this mass action assumption. Okay, so thinking about this as a model, and I said earlier that we think about this as a set of equations. So let's write down the equations that would describe this SI model. Okay, so we have the number of people that are susceptible, we have the number of people that are infectious, and then we think about how the number of people susceptible and infectious change over time, and then we write down what is called differential equations to describe this. Okay, who of you knows what differential equations are? Quite a number of people. Okay, some people don't. So if you don't know what differential equations are, I won't explain it to you, but I will explain to you how they work. Okay, so what we do is we write down equations that describe how the number of people in each of these compartments change. Okay, so for example, we do this for the number of susceptibles, and the way we write this, and if you don't know what a differential equation is, then just think of this as a slightly funny notation. So we write this as the S over dt, and that describes how the number of people that are currently susceptible changes. And the way this changes is, well, it's negative because people start off as susceptible and become infectious. No one ever goes back the other way in this model. Okay, so we take away people from the susceptible compartment and put them in the infectious compartment. And then we think of the rate at which this changes, or how many people turn from being susceptible into becoming infectious over time. And this is simply the force of infection. So that we said what we said is the force of infection earlier is the probability per time that a susceptible person becomes infectious. And that's exactly this. It's the change per time in the number of susceptibles for each susceptible, and then we multiply it with the number of susceptibles, and we get the total number of people that turn from susceptible to infectious in a given time at a given time step. And we do the same for the number of people infected, and that's the same simply with plus, because the people who are susceptible turn into infectious people. Okay? And we said earlier that we can write lambda as this beta times I over n, so it's just another way of writing this is we can also replace here lambda by beta times I over n. Okay, so we know at any given time how many people at the moment are going from susceptible to being infected. Okay, and then we can use these equations to simulate our model. And we can put these equations in a computer, and we'll show you tomorrow how that works, and then tell our program to simulate this SI model. Okay, so how does that look? So you've got the equations up here, and what I'll show you here is over time. So we go left to right over time, the number of people that are susceptible and infected. And we'll have 1,000 people in our population, and we'll start off with 1 infected, so it's down here, and 1,000 susceptibles. Okay. So what happens? Well, as we said, over time, so we evaluate this at every time step, and what happens is that people become from susceptible, they become infectious. Okay, very simple. All right, well, this is what we did with the standing epidemic. We start off with 1, and at the end, you have everybody infectious. Almost everybody was infectious. Some people escaped, but yeah, almost everybody ends up being infectious, and so everybody in the population ends up in the I compartment. And if we try different values of this beta, so this is beta, just said beta to something, 0.5, and then if I set it to 1, so if I have a higher infectious rate, then this will happen quicker. Okay, so that the infection spreads more rapidly. And so the time it takes until everybody gets infected depends on this value for beta. Okay, and so we said we have a model here, the SI model. Well, actually, does this make sense to people? Does anyone have a question at this point? Okay, makes sense, sort of. Okay. All right, so let's think about the SI model. And does someone have a question there? No? Yes? No? Maybe? No? Okay. Think about the SI model. Okay, so I said it's the simplest model. It's a very simple thing. Just something happens. So just everybody in the population gets infected. Okay, the time it takes depends on this infection rate. Can you think of any infection for which this is a good model, apart from the standing epidemic?
I can suggest a bad one.
Say again?
I can say which is a bad model. Influenza.
Influenza would be a bad model. Why? Or it would be a bad model for influenza. Why?
Because I think it will, there is too much of cross-reactivity amongst different influenza strains, because of which you cannot possibly have 100 maximum of S and maximum of I
Right.
at any time.
Right. So there's too much cross-reaction. So people have immunity of sorts, says the immunologist. Great. Yes. Yeah. Okay. It's a bad model for influenza. Can anyone think of an infection for which it might be a good model? Say again. Sorry. HIV.
SI models are good for HIV.
HIV. Okay. Yeah. So it's a good point. It might be a good model for HIV. in that, you become infectious and then you stay infectious. And
Yes, stay infectious.
Yeah.
Stay infectious the whole period.
yeah, that's right. So that's right. It's a good suggestion. The thing that's usually complicated with HIV is what I said earlier, is this change in viral load. So you're very infectious in the beginning, and then you become much less infected. So it's right, you would use something like an SI model, but perhaps some variation in there in where somehow you reflect it. But yeah, it's a good suggestion. Anyone else have a suggestion? Okay, well, it's actually really hard to think of an infection for which it's a good model, and well done for thinking of HIV. I try to have a bit of a look around on the internet to find a virus for which this might work, and I found two that are really not particularly relevant, I think, for public health, but nevertheless interesting. So there's two. One's called the cytomegalovirus, and the other one is herpes simplex virus, and they're both viruses that most of the world population are believed to have. So, but they are mostly benign, so they don't do any harm to you. So cytomegalovirus only does harm to you if already you have a very weak immune system or some kind of other problem. And herpes simplex virus also most people have, but it mostly lingers in your body, and then it only at times it becomes active and infectious. Okay, so it's a simple model, but it doesn't describe many diseases very well, and the ones that it does are perhaps a bit obscure, or like with HIV, you have to think about, make it a bit more complicated. And so let's think about how we could build a more realistic model or a better model. Okay, and we said that in the SI model, we assume that people who get infected are infectious forever. Okay, and so one way to think, or in fact, for most infections, there's some kind of immunity. So you have an infectious phase where you have symptoms, but then you recover, and you can no longer be infected, and you're no longer infectious. And if you think of, for example, flu, as was mentioned earlier, or measles, then this is definitely the case. And so what we can then use is we can put this in our model. Okay, so we had the SI model earlier, and now we have recovery, and people after becoming infected become recovered and are then no longer infectious, but also can't be infected. Okay, so if you have had an infection with influenza, then you can no longer be infected with that strain of influenza, and also you recover. So you're not infectious all the time. And similarly for example, for measles. Okay, and so we say R now is the number of recovered or immune people. And in fact, the SIR model is, I think, what's usually considered the most famous infectious disease model, and what a lot of infectious disease models are based on. You don't often see the SIR model, but you see very often the SIR model, which goes back to the 1920s to a paper by two people called Kermack and McKendrick, who were actually describing an outbreak of plague on the island of Bombay in India. Okay, and they wanted to test. So they saw that there was this outbreak which started and ended again, and they wanted to know whether it had ended because something changed about the infection. So whether there was some kind of evolution where the infectious agent became less infectious, or whether it had something to do with the fact that there were no more susceptibles on the island of Bombay for the infection to infect. And they tried that using this model, the SIR model. Okay, so we say R is now the number of recovered people, and we call gamma, so new letter here, is the recovery rate or the probability of recovery per unit time. Okay, so, and this is simply the inverse, or 1 divided by the duration of infection. So if an infection is 5 days long, then this probability of recovering is 1 divided by 5 days, so 1 over 5. Every day you have a probability of 1 over 5 to recover if it's a 5-day infectious period. Okay, and so we can do the same thing as before. We can write this down as differential equations, and so we have the number of people susceptible, we have the number of people infectious, the number of people recovered, SI and R, and we think about how does this number change over time, and we write this down as differential equations. Well, for susceptibles, nothing changes, so this is still minus lambda times S. For infectious people, you still have people becoming infected, but now there's this new term compared to the SI model, and this is recovery, so people become from susceptible become recovered. Okay, and then we also have a new differential equation, which is for recovered people, and so it's simply this here. It's the people who leave the infectious compartment become recovered, and they enter the recovered compartment. Okay, and again, as before, we can rewrite this using our notation of before. Nothing about that changes, and we simply rewrite this with the beta I over n for lambda. Okay, and we can do the same as before and look how this behaves over time. Okay, and we start exactly the same as before. We start with everybody susceptible except for one person, and you have one infected down here in red, and there's 0 recovered, so you can't really distinguish these two. And then you have this over time, and you have the number of people infectious increasing, if I go back a bit, number of infectious increasing, number of recovered people is also increasing because people become infectious and then they recover, and then the number of susceptible is decreasing. Okay, and then you have this peak, so the number of infected or infectious people peaks, and at some time drops again to 0. Okay, so again, blue here is susceptible, red is infectious, green is recovered, and differently to the SI or in difference to the SI model now, what you see is this green line here. It's actually below the whole population, and at the end you have some susceptibles left. So now not everybody in the population gets infected. Some people stay susceptible until the end, and you have this effect that the infection peaks and then goes away again. And if you use different values for this beta and gamma, so this is here again I just plugged in some numbers, beta and gamma, and if I change them, so if I use a higher value for beta, so go back again, so it's beta equals 1, and I double it, then you have a peak which is higher and quicker. Okay, so you increase the infection rate, and you have a peak which happens earlier and is higher. And more people at the end are recovered, and there's only a few susceptibles left on this occasion. And then I don't have that actually. Okay, so the time and the height of the peak we said, and the total number of people infected, or the total number of people that get infected depends on now the beta and the gamma. Okay, and then the other thing is, again, in contrast to the SI model, is you can have a situation where almost nobody gets infected. So now here I've chosen some parameters where I've chosen a much smaller beta, and now there's no outbreak that happens. Okay, and again, this is the difference between the SIR and the SI model. Okay, and this gets me to the basic and what's called the net reproduction number. So I introduced the basic reproduction number before, and just to remind you, this is the same slide as before. Basic reproduction number is the average number of secondary infectious cases that results from the introduction of a single infectious case in a totally susceptible population. And we can now look at what this is in the SIR model. Okay, so all right, let's work this out. We have this definition. All right, what do we have in there? We said it's the introduction of a single infectious case. So what we do is we set I to 1. Okay, a single infectious case. We also have a totally susceptible population. So we say that S is N, or really, okay, so technically it's N minus 1 because we've made one person infectious, but it's approximately N. If it's a large population, then this 1 won't make a big difference. We can say S is roughly N. Okay? And then the last thing is that we said, okay, so we have this equation for the force of infection. And so for a single infectious case, well, we can work this out then. So I is 1, so this is simply beta times 1 over N. So the number of secondary cases per time, so remember the lambda is the probability for a susceptible person to become infected per time. Okay, so the total number of people that become infected per time is lambda times S, but S is N, and if we put that in, we simply end up with beta. And so, and then if you think of the total number of secondary infectious cases generated by this first person, we have to multiply this with the duration of infection. Okay, so this is per time. This is the number of people that the first person infects per time. And for the total number of infectious cases, simply beta times the duration, or the duration we said is 1 divided by gamma is beta over gamma. So we've related the basic reproduction number to the parameters of our SIR model, and we know now what is the basic reproduction number in the SIR model. Okay, and we can link these two things. And so if we look at what this means in the SIR model, well, we have this equation for the change in the number of infectious people, di divided by dt, and so this is simply the equation we had earlier. So it's the people who become newly infected minus people who become recovered. Okay, and now we have this expression for R0. So if we start with a single infectious person, so we have again I equals 1, S is approximately n. We put this in, and then so if S is n, then this is simply beta I minus gamma I. Well, I is 1. This is simply beta minus gamma. And we can rewrite this if we divide this, if we take out 1 over gamma, so we divide both of them by gamma and take this out, then this is the same as 1 divided by gamma times R0 minus 1. Okay, so initially, so if we start with a single infectious person, then initially the change in infectious people is that, which means that if R0 is greater than 1, this will be positive, and the number of infectious people will increase. And if R0 is smaller than 1, it is negative, and the number of infectious people will decrease. So just like we said earlier, intuitively, we have this confirmed in the SIR model, is that this value of R0 tells us if a newly introduced will spread or if it will die out, whether the number of infectious people will increase or decrease. So it's kind of like a check of the way we link these two here makes sense. Okay, so this is what we said happens in the beginning. Completely susceptible population and a single infected person. And so I showed you, this was the simulation I showed you earlier with beta equals 2 and gamma equals 1. So R0 is beta divided by gamma here is 2, and this is what you had. And then the other simulation I showed you was this one, where beta divided by gamma is a half, it's smaller than 1, and there's no outbreak. Okay, so this is what tells us whether with our parameters we're in a situation where there can be one of these, where there is an outbreak or there isn't. Okay, and a related concept, which is important and often more useful, is what is called the net reproduction number. And if you look at the definition here, so the net reproduction number is the average number of secondary cases that results from each infectious case in a given population. So it's not anymore a single infected person where everybody is susceptible. Now you actually look at something that where you just look at the population at any given time, and you look at the average number of people that someone infectious will infect, and this will change over time, right? So in the beginning, perhaps this number could be higher, and then later, when there's immunity building up, it could be lower. So we're not anymore only at the beginning of an outbreak, and we're not anymore in a completely susceptible population. Okay, so let's work that out. So we have this force of infection, or the probability for a susceptible person to become infectious per time, and then again, just like before, the total number of secondary cases will simply be lambda times or this force of infection times S. So it's the probability of everybody to become infected times the number of people is the number of people who get infected per time. And note that unlike before, this I stays in here, so we're not setting I to 1 anymore. We're now saying, okay, this is an infection which is spreading in a population, and you just want to know at any moment in time how many secondary cases will one case generate. And again, just like before, if you want to look at the total number generated at any point in time by infectious people, we multiply it by D, and then we want to know the average. So this is at any point in time, how many new cases of infection get generated, or how many new cases get generated. But now we want to know the average number for each infectious case. So we divide this by the number of infectious people, and we get what is called the net reproduction number. So we have this here, we divide it by S, and we divide by I, and we get to this expression here. So we divide this by I as beta divided by gamma times S over N. So it's R naught times the proportion of people that is currently susceptible. That's the number of people that everybody will, or on average that everybody will infect at any given point in time. And so that's just what I just said in other words. And so if we look at this, again, just like before, we look at the differential equation for number of infectious people, have the same thing as before, but now we're not anymore setting I to 1 and S to N. We're saying that we're leaving these, and we say at any point in time, well, again, we can rewrite this, so we can divide by gamma here and take it out, and we get that this should be I divided by gamma, but it's importantly, it's proportional to Rn minus 1. So at any point in time, the net reproduction number tells you whether at this point in time, we're not anymore looking at the beginning of an epidemic, but at any point in time, whether the infection is increasing or decreasing. Okay? And if we look at our SIR model over time, so this is here what the reproduction number does. Again, this is exactly the same that I showed you before. So it starts with 2, and in fact, in the beginning, if everybody is susceptible, we said the net reproduction number is the basic reproduction number R naught times the proportion susceptible. So in the beginning, when everybody is susceptible, the two are the same. Okay? And we said here R naught is 2, so in the beginning, the net reproduction number is 2. But then as more and more people become immune, this number drops, and then it crosses 1, and the point in time when it crosses 1 is exactly the point when the number of infected stops increasing. Okay, so we said before, this number tells you at any point in time whether the epidemic is increasing or decreasing. So it stops increasing when it's 1, it turns over, and then the reproduction number here is smaller than 1. So this tells you how many people on average people are infecting at any point during the epidemic. Okay, so at the beginning they're the same, and then at the peak it's 1. Okay, and so there's an important concept related to this, which we call the herd immunity threshold. And if you think of this, if you think of an infection and you think of a situation where you can vaccinate people to prevent an outbreak, then vaccinating people simply changes this fraction here, this proportion of people susceptible. Okay, so you make people immune, and you have a smaller proportion of the population that is susceptible. And so you can ask how many people do you need to vaccinate so that there can't be an outbreak? Okay? So, well, what this means is we need to vaccinate so many people that the net reproduction number becomes smaller than 1. Okay? And to reduce the number of susceptibles to a degree that the reproduction number is smaller than 1, you can work out that you need to vaccinate more than 1 minus 1 over R naught. Okay? So you simply you look at the number of susceptibles, you look at S over N, and so you want Rn to be smaller than 1, so you can divide this by R naught, so the proportion of susceptibles needs to be smaller than 1 over R naught, and to get that, you need to vaccinate more or equal to 1 minus 1 over R naught. Okay, so you can work out, using this theory, you can work out how many people you need to vaccinate in order to prevent an outbreak. And so this proportion of people that you need to vaccinate is called the herd immunity threshold. And the important thing here is that to stop outbreaks, you don't need to vaccinate everybody. Ideally, you would always vaccinate everybody because you protect them from becoming infected. But in reality, usually it's difficult to vaccinate everybody, and people might, for some reason, choose not to be vaccinated, or people might have underlying conditions that it's risky to vaccinate them. But you only need to vaccinate this proportion of people in order to stop outbreaks. So for example, if R naught is 2, as we saw earlier, then this is 1/2, and then 1 minus 1/2 is 1/2, so you need to vaccinate half the population to stop outbreaks if R naught is 2. If R naught is 20, or say if R naught is 10, something which is more like measles so then this is 1 over 10, and then 1 minus 1 over 10 is 9 over 10, or 90%. So for an R naught of 10, you need to vaccinate many more than for R naught equals 2. You need to vaccinate 90% in order to stop outbreaks. And So you can look at this herd immunity threshold, and we said R0 is different for different diseases, and so you can work out for different diseases what this herd immunity threshold is. And we said malaria, it can be R0 can be up to 100. So you really, even if you had a working malaria vaccine, you would have to vaccinate almost everybody in order not to have outbreaks of malaria anymore. Whereas with measles, it's more like 90 to 95%, and then for flu, you only need to vaccinate about half the population because R0 is 2. Okay, and so as a last bit about the SIR model, so we can think again about what it is a good model for. So it's different now to what we had earlier in the SI model, and we have a model where not everybody in the population always gets infected. And also, you have this threshold where if R0 is greater than 1, infection spreads and then dies out, and if it's smaller than 1, you can't have outbreaks. And so again, you can think about for which infections it's a good model. And I told you earlier that the original application was to the plague in Bombay. So you had and that was in about 100 years ago, and you had this where you had this increase and then this decrease. So I don't know if you can see that there's some data points here, and then this is the fit to the outbreak. So it looks like it might be a good model for that. Okay, and you can think of other things. So here's a time series of measles. So measles, of course, confers lifelong infection. Okay, but then this looks a bit funny. So you have these outbreaks here, and then there's outbreak, outbreak, outbreak. All right, we'll get back to that. Maybe it's a good model for that. Really, we only had a model here where there's one outbreak and then it goes away again. So perhaps it's a good model for this time period here, but not for the whole time series. And you can think about whether it's a good model for influenza, for example. And we talked earlier about influenza, and we mentioned that it's complicated with the immune system, and so you always have some immunity in the population against influenza. And so you don't necessarily have this lifelong immunity, and you have to think about which particular strain is spreading and so on and so forth. But it's generally a model for one outbreak of something that's not usually in the population. Okay, and I think before I go on, I think let's just have a quick 5-minute break or so, and then we'll go on. In fact, before we have a 5-minute break, does anyone have any questions at this point? Is anything unclear? Yeah. Say again, sorry? Will this model work?
Will this model work for tuberculosis?
What do you think? Will it work for tuberculosis?
It shouldn't, because we need one more arrow from recovered to infected, right?
That's right. So you can be latently infected, so you are a bit like someone recovered or something, but then you can go back and become actively infectious.
So
again.
there'll be like 2 more arrows, right, from both the states, I think, because even a cured tuberculosis person is susceptible to infection.
So you need 2 more arrows. So which arrows do you need?
R2I and R2S.
R2S as well. Okay.
Because they can be susceptible also.
They can become infectious and then susceptible again.
Yeah. So.
Okay. I'm not an expert on tuberculosis, but as it happens, Gwen is, and we'll have a lecture on tuberculosis modeling on Wednesday, and I'm sure you'll have your suspicion confirmed, and then that the SIR model that you need more arrows. Yeah. Okay.
So how is this a model for something like malaria, which involves a vector?
Okay, so how good is this as a model for something like malaria, which has a vector, is the question? Yeah. Well, it can be a good model, but of course, so what you can do is you can as a starting point, you can ignore the vector. If you can say, okay, you have this beta, this infection rate, which somehow tells you how likely you are to get infected by someone else, and if the mosquito doesn't have any own dynamics, then often you can get away with this. The problem is that in reality, the mosquito populations are usually seasonal, and so you need to have so what you can do, you can have an SIR model, and then you have a parallel SI model. Usually it's an SI model because the mosquitoes don't recover for the mosquito, and then you can have infection going back and forth between the people and the mosquitoes. And that allows you to then put in something like seasonality or into the mosquito population. It also tells you how effective your control strategies are on mosquitoes, if you have bed nets or insecticides. And so it depends a bit on what exactly you want to look at. If you're only interested in human infection and you're not interested in mosquito control, and your mosquito populations are stable, then you might be able to get away with something like the SIR model. But then also immunity is complicated, I guess, with malaria. You have reinfection and things. So you have to think about it a bit more carefully then. So
any mosquito control, like whatever strategy you take, will only reduce the beta.
So sorry, is what you're saying? Any strategy on reducing the mosquito population will only reduce the beta. Yeah. But you can look at, for example, what people have done is look at the difference between doing control on the larvae or on the adult mosquitoes. So sometimes you have to distinguish. But yeah, it's true. I mean, if all you want to look at is the effect of a reduced mosquito population, then you will probably again get away with not explicitly modeling the mosquito population and just having a change in beta. Yeah, that's a good point. Any other questions? Yeah. How would you capture what?
Environmental variations like temperature, humidity, and so forth.
Temperature, humidity, and so forth. So this is going back to malaria or any model. Well, okay. Things like, okay. I mean, there's a number of things. So as a starting point, if you think about vector-borne diseases, then you have this. You would have to somehow explicitly model an effect on the vector population, on how the mosquito is affected by the climate. So, for example, you might have, as I said earlier, for something like malaria, so you might have an SIR model for human populations and then a parallel SI model for mosquito populations where the mosquitoes die after a while. So they become infected and then they die. And so the mortality of mosquitoes or the birth rate of mosquitoes might then depend on climate. And if you know how this depends on climate, you can put this in as a factor that affects your birth rate parameter in the mosquito populations. For non-vector-borne diseases, it's not often that we think of climate or humidity as being important. It might be important for flu, for example. I mean, we have some idea that humidity plays a role for flu in a seasonal kind of way, and so what people often do is you put in what's called a seasonal forcing. So what happens is that your beta becomes a sine function, with an annual cycle. So it becomes lower in the summer and higher in the winter, and so you modulate this, and you do this in a way that it fits your time series. And another factor that comes in there, for example, is the school year. So for childhood infections, what people often do is they have some kind of infection rate which drops when there's a school holiday and then go up again. And then this can tell you something about, or this can help explain why maybe infection rates go up or down. Okay? Any other questions? All right, let's have a 5-minute break, and then we'll get to the last half hour or so of this lecture. Okay? Okay, I've switched it on here. Should be okay. Okay, so yeah. Okay. Yeah, we were just talking actually because I said that the SI model is a good model for the standing plague, but actually thinking about it, it's more like an SIR model because you stood up and then you pointed at 2 people, but then you didn't keep infecting other people. Whereas the SI model, you would stay infectious for the whole period and you'd keep infecting others. Whereas it was more like, okay, you infect 2 and then you stay out. You don't become infected anymore, but you also don't infect 2 others. So you're almost like a recovered in the SIR model. So perhaps the standing plague was more SIR model. Can I just ask before I go on to the last half hour, how is this going so far? Do people think it's too fast, too slow, or just right? Who thinks it's too fast? Okay. Who thinks it's too slow? Okay, who thinks it's just right? Okay, great. Thank you very much. Okay, great. Then we'll go on like this if it's just right. Okay, so far we've only looked at outbreaks or something that spreads and then infects everybody, and then that's it. And of course, we have many infections that are endemic. And I mentioned earlier that malaria is endemic in many places, and there are many others that can. So there's infections that can become established in a population and spread, as we say, endemically. And if you think about back at the SIR model, so what happens in the SIR model is people become infected, then recovered, and then that's it. And if you think back at the net reproduction number, this Rn, so we said Rn is R0 times the proportion susceptible. And R0 is a fixed number for the disease in the population. It doesn't change. But the proportion susceptible goes down until the net reproduction number is 1. You have this peak, and the number of susceptible. Actually, I can show you the graph again to make this clearer, perhaps. Here. So the proportion of susceptibles goes down until Rn is 1, and then keeps going down. So there's this. So you have this turnover, this maximum when it's 1, and then epidemic declines as the proportion of susceptibles declines. And I said, so Rn, this is simply R0, which is a constant, it stays the same, times the proportion of susceptibles. So this really is a curve for the proportion susceptible. And so if you think about what happens here and why this infection doesn't stay in the population, why it has a peak and it goes away again, it's because it runs out of susceptibles. It's because there are not enough susceptibles in the population to keep the net reproduction number above 1. And so for something to become endemic, there needs to be something going on that this doesn't happen. So there needs to be something going on that there are always enough susceptibles in the population that the infection can keep spreading. Okay? So let's go back here. So for this to happen, so we need to find new susceptibles. Okay. So how could there be new susceptibles? Question to you. Yeah? Inflow of people, right, like immigration or some kind of population exchange or something like this, right? Very good. Yeah. Any other suggestions? Say again, sorry? Right. So people could lose their immunity. Yeah. Very good. Any other suggestions? New births? Newborn babies. Right. Perfect. Okay. So you've got exactly the 3 things that I managed to come up with. So we have births, and in fact, the notion that we have childhood diseases like measles or chickenpox, the reason they are childhood diseases is because you get them only once, and then you're immune for the rest of your life. And it's the newborn susceptibles that get it. They're infectious enough that it doesn't take your whole life to get it. The first time you get it, and they're infectious enough that you become exposed to them sometime early in your life, and they're childhood diseases. Okay, so new births. You have loss of immunity for many infections, cholera being one example, but there are many others. And you can have something like immigration, which we tend to ignore a bit. It's not usually a significant factor, but it's in some cases it is. But we won't talk about this, but I'll talk about these two, about births and about loss of immunity. Okay. So if you have loss of immunity, so you add an arrow from R to S with a certain rate, which is called delta here, then you add, I meant to say, I will put these slides online, and you can download them. So you're welcome to take notes, but you don't have to copy them literally. You can look at them later and look at what was in there. Okay, so what I said is so people can lose their immunity, so people can go from R back to S and can become infected again. For some infections, with a certain rate or after a certain time, you lose your immunity. And then this is called the SIRS model, because you can go SIR, but then you can go back to S. Of course, then you can also go back to S, to I and R, but you can't call it the SIRS model. So you just call it the SIRS model. And this delta here is then, just like we had before, the recovery rate is the rate at which you lose immunity, or again, the probability of losing immunity per time step. And this is simply the inverse of the duration of immunity. So if your immunity is 5 years, then your probability per year of losing the immunity is 1 divided by 5. Okay? And this is our delta, our rate of losing immunity, 1 divided by the duration of immunity. And okay, so same exercise as before. We write this down as differential equations. So we ask ourselves, what is the rate of change of susceptibles, of infectious, and of recovered people? And so now for the susceptibles, we have an arrow leaving still for people who are becoming infected. So you have this minus lambda times S. But now you also have some people who become susceptible again. So there's a positive influx, a positive change of susceptibles. And this is simply delta, the rate at which immunity is lost, times the number of recovered people. Okay. For the infectious, it's the same as before. You have the newly infected people coming in, recovery going out. So it's plus lambda times S minus gamma times I. And then for the recovered, you still have the influx of people who are infected and become recovered. But now you also have a new term, which is the people who become susceptible. So this minus delta times R. Okay. And just like before, we can write this in terms of beta and I. And then, again, we can simulate that. So this is our equations here at the top. We start, as ever, with 1,000 people. We have 999 susceptibles and 1 infected. And what happens now? Okay, so it looks a bit like the SIR model. But now, actually, what happens is that it doesn't go to 0. Okay? So in the SIR model, this would then drop. But now, because people lose their immunity, people go back from R to being susceptible and then can become infected again. And what happens here is the infection stays at this level in the population. Okay? So, in other words, the infection becomes endemic. We have a model for an endemic disease with the SIRS model. And if we look at different values, so again, so we have delta here is 0.5. If I put delta to 1, or I increase the rate at which immunity is lost, which is the same as to say I make it a shorter duration of immunity, people lose it quicker, then that level becomes, just flicking back and forth, that level becomes lower. Okay, so then the level of infection is a bit higher now. So if people lose their immunity quicker, it makes sense, the level of endemic infection is higher. And then if I change, what have I changed here? If I make it even smaller, then so if I make it smaller so people stay immune for longer, then this level is lower, and the level of people who are immune is higher. Okay, so that makes sense. So people have longer duration of immunity, the endemic level of infection is lower. Okay, so the number of people that are infectious at any time, or also the number of people susceptible or recovered, the endemic level somehow depends on the interplay between these parameters now. Obviously, if I increase the infection rate, the level of endemicity will be higher, and if I increase the recovery rate, it'll be lower again, so it'll somehow be a combination of these three things. Okay, and then if I set delta to 0, so if the rate of losing immunity is 0, that means people are infected, immune forever, then I'm back to the SIR model. So in some ways, the SIR model could be seen as a special case of the SIRS model, where the rate of immunity loss is 0, or is so small that it could be seen as 0. Okay, now if we look at the net reproduction number in the SIRS model, and just following it up over this simulation that I showed you earlier, again, we start with the net reproduction number being the same as the basic reproduction number, because everybody is susceptible. And then it drops, and then what happens here, it just it stays at 1. Okay, so the endemic level is exactly the level where everybody on average infects one other person. Then you have a stable situation. If everybody infects one other person, then you don't have an increase, you don't have a decrease, you have this endemic level. And this is what happens in the SRS model, is you go to exactly that endemic level. Okay, so in the beginning, net reproduction number is the same as the reproduction number, basic reproduction number, and at endemic level, it's 1. Every infected person causes one other infection. Okay, so thinking about infections for which this is a good model, so maybe you can have a think about what could this be a good model for? Any ideas? Cholera? Yeah. good point. I think I have that there. Yeah, it's a good model for cholera. Cholera is the thing that can be complex about cholera is that it's also, it can stay in the environment. So it can stay in water sources, and so even once people recover, I mean, you could have a water source becoming infected through people, and then people recover, but the water source stays infectious. So what people sometimes do is have a model which is an SIRS model, and then also have a water component or something where people can infect water and recover again or something. Okay, what about measles? Okay, measles not really, because measles, there might be some waning of immunity, but if there is, it plays such a small role that pretty much once you've had measles, you're immune for life. But in measles, we still have something like endemic measles. And in fact, if you look at measles, so this is apart from a child with measles, this is a time series of measles in the UK. Okay, so this is when vaccination came in. So ignore what's on the right here for the moment, because we're not talking about vaccination yet. But you have this situation before 1968, when vaccination was introduced, where you had these outbreaks every 2 years. Actually, there was an outbreak of measles. But measles confers lifelong immunity, so you don't really have an SIRS model. It should be SIR model, and you have these 2-year cycles. Well, of course, what we said earlier is it's a childhood disease, and you have you get new susceptibles through births. Okay, and then you have these funny 2-year cycles. So let's have a look at a model which is an SIR model, but we include births and see what we can get, whether we can use this to describe what's going on here with these funny outbreaks. Okay. So our last model for the day is an SIR model, which has a couple more arrows. In fact, we have what we call vital dynamics or demographic dynamics, because we have births and deaths. So you have a new arrow in here, which is births. So there's a birth rate, which I call new here, and the birth rate is in a simple assumption is proportional to the population, or the number of births is the birth rate times the population size. So the birth rate being the average number of newborns generated per person in the population in a given amount of time. Okay, and then also you have a death rate, and we're talking about an infection which doesn't necessarily kill people. So like measles, it has a very low death rate, but this is a death rate which is just a general death rate in the population. So it's just people dying of old age or something. And so it's the same whether you're susceptible, infected, or recovered. All of them have a death rate which is mu. Okay, so we have this per capita birth rate nu, which is simply the per capita birth rate nu, and they have mu, which is the per capita death rate, which is the inverse of the life expectancy. So just like before, the rate of something is just 1 divided by the duration of the same thing. So the death rate is 1 divided by the duration of a life. Okay, and if they're the same, if the death rate is the same, the death and the birth rate are the same, then we would expect our population size to stay the same, whereas if the birth rate is greater than the death rate, we would expect our population size to increase. And if the death rate is smaller than the birth rate, you have sorry, this is the wrong way around. If the birth rate is bigger than the death rate, okay, so this is the wrong way around. This should be if nu is smaller than mu, then the population size decreases.
Yes, mu is more than mu than population.
Exactly. So, but this is the same as that. It's just I just flipped the letter. So it should be if the birth rate is smaller than the death rate, then the population shrinks. Okay. Anyway, you know what I mean. Okay. So let's again, just like before, let's write down our differential equations for the SRR model with births and deaths. And so thinking about susceptibles, so now you still have people becoming infected, and now you also have an influx of newborn, and then a decrease because of deaths. So you have an increasing term here, which is the newborns, and then you have a decreasing term, which is the death rate. Okay, so you lose susceptibles through infection, you gain them through birth, and you lose them again through death. Same with the infections. Okay, so same as before, just that you have a death rate. And similarly with the recovered, you have a death rate. And there's nothing going from R to S directly, so there's no loss of immunity. Okay? And just like before, so let's have a look at a simulation of this model. Okay, so and we start off with everybody being susceptible. In fact, what happens here is there's a big outbreak in the beginning where a lot of the population gets recovered. And then what happens is over time, people start, recovered people die. Okay? Recovered people die, and so you have and you have newborns in the population. So of course, recovered, susceptible, and infected all die, but then they all end up back in the susceptible compartment through births, and you have newborns until you have an outbreak. So there's a small blip here of I, which I'll show you a zoomed-in version of that in a second. Which then, so some of these susceptibles, in fact, this many susceptibles, become infected and then recovered. So you have an increase in the recovered and you have a decrease in the susceptibles. And then the number of susceptibles starts increasing again, number of recovered starts decreasing again, and you have another blip here. Okay, and so on and so forth. Okay, and in fact, if we look at this in more detail, so now I'm zooming in, so now this is from 0 to 50, and this here was from 0 to 1,000. I'm just zooming in on the red line. Okay, so you have an outbreak in the beginning, and then another outbreak, another outbreak, another outbreak, and so on and so forth. Okay, so you have some kind of idea of cycles going on now. And in fact, yeah. I will get back to you on that. So, okay, so the height of the red line is decreasing over time, and we'll come to that. Okay, so again, I can change the parameters, and I can make these the distance between them longer, and I can make them higher, and again, so it depends on our parameters, what's going on here. So from here to here, if I increase the birth rate, then you get many more cycles, and so they're closer together. And here, if I decrease in fact, that's quite interesting. So from here to here, so here beta is 500, and here beta is 250. So from here to here, I decrease the infection rate, but I actually get higher outbreaks. Okay, so that's interesting. So this goes up to 45 here and up to 20, whereas this one goes only up to 15 and then smaller. But you have more frequent outbreaks. Okay, so with a higher infection rate here, you have outbreaks more often, but they're actually lower in size. Okay, so what's going on here? Let's have a look at this in more detail. So you have this. So here I used a measles-like R0 of 10, and you have the net reproduction numbers going down and then up and down and down, up and down, along with the proportion of susceptibles. And so this is now going up and down. It's oscillating around 1. And so if we have a closer look at this, then what we see is in the beginning, so you have this outbreak, and then so you have a situation here where there's very few susceptibles. Okay, it's almost zero. There's just a few susceptibles in the population. You've had this outbreak, so there's hardly any infected in there, and then because there's so few susceptibles, the net reproduction number is smaller than 1. In fact, this first bit here, this is just like an SIR type outbreak, just like what we saw before. It increases until Rn is 1, and then it goes down again, and at the end of the outbreak, the net reproduction number is well below 1, and there's not many susceptibles left. And remember that here I said R0 to 10, whereas before it was always 2. So you have this very quick, very early outbreak here, and then you end up with a net reproduction number smaller than 1. And then what happens is that the number of susceptibles is increasing because of birth, and with the number of susceptibles, the net reproduction number is also increasing. But it's increasing, but it's not yet, it's still below 1. So you have no outbreaks. Okay? So the number of susceptibles increases, but no outbreak. It increases up to a point where it crosses 1. And that's when you can't really see it here because it's quite low, so it just looks like a straight number. What really happens here is it goes down, 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 and then it starts slowly going up again. Okay? So it's just 1, so you're just getting to a stage where you can have an outbreak again, and then it starts being slightly bigger than 1, so you have a slow increase here. Okay, so now the net reproduction number is greater than 1, number of infected people increases, number of susceptibles still increasing until you get to a level of Rn which leads to this big outbreak. The number of infected increases rapidly now. You have a peak in susceptibles, and then because it's now you have this critical mass of susceptibles that you can have this big outbreak again. R0 is large, Rn is large enough to have a proper outbreak, and the number of susceptibles decreases. Okay, because people become infected, and with the number of susceptibles, the net reproduction number decreases, and again you have a peak in infections. Okay, and then the cycle begins again. You have exactly the same again. You have very few susceptibles, and you have another outbreak. Okay, and then this happens here again and here. So it's always you have an outbreak which burns through the susceptibles, leaves very few susceptibles left, so that the net reproduction number is really small, and you're far away from a situation where you can have an outbreak. Most of the population is immune. And then through birth, you have this slow accumulation of susceptibles until there's enough susceptibles that you can have another outbreak, and you get another outbreak, and the thing starts again from the beginning. So now there was a question, so what's happened? This is decreasing over time. And in fact, if we look at the data again, this didn't seem to be decreasing over time. This produced relatively stable oscillations. And in fact, what you can show is that what you get with the SIR model, even with births and deaths, you get what is called damped oscillations. You get oscillations which become shorter and smaller over time. And in fact, eventually, if you keep going with this, you would end up, well, I can show it here, you would end up again with an endemic level. So it's a better description of measles than the SIR model, but it's not a perfect model. In fact, what happens is that you need something else to have something else in the dynamics, some other oscillations that somehow pushes this up every time to the previous level. And so, again, as I said, SIR model with births and deaths, you have this decline over time. And to get these stable cycles, you need what I mentioned earlier. You need some seasonal forcing. You need something else that somehow pushes the number of infected up, and in fact keeps it down in some kind of periodic interval. And what you can show is that if you put seasonal forcing into the SIR model with births and deaths according to the school year, then you get these stable oscillations that are at the same height every time. Okay, I'm not showing you this model now, so you'll have to trust me on this that it works. And in fact, you can work out what this period is, so how often you get the cycles. You can work this out from the birth and death rate, and because as I mentioned earlier here, so these were 2-year biannual cycles, and you can work out by looking at the birth rate in the UK at the time and the duration of infection, you can work out that you would expect 2-year cycles. Okay, and you can look at a number of different settings. If we look back again, so here this depends on R0 and on the birth rate and on the duration of infection. So it'll be different for different diseases. And you can look at, so this is for different infections and for different places, what has been calculated to be the number of years between epidemics, and then what has been observed, and you can see that it's in relatively good agreement. So I said UK is about 2 years, and that's what you would expect from the theory, and that's what's been calculated. But then if you take something, for example, which has a lower R0, like rubella, you have cycles with a longer period, so something like 3, 4, 5 or something in the UK. And again, so for example, smallpox in India, it's been calculated that it should be 4 to 5. There should have been, before vaccination between 1868 and 1948, should have been an epidemic every about 4 or 5 years, and there was an epidemic every 5 years. And you can simply work that out from the interplay between the birth rate, so the rate at which you get new susceptibles, and R0 of the disease. Okay, and so I just want to briefly, to finish off, I want to talk about further extensions that you can make to models, and so, for example, you can look at things like maternal immunity, which plays a role for chickenpox and measles. So what you would do is, or also for other infections. So what you do there is you have when people get born, initially they end up in some maternally immune compartment, and then after a year they become susceptible, for example. So you can just imagine how you would add that. Instead of, in our model, we had new births going into susceptibles, you would have some intermediate compartment where they go into, and then they become susceptible, and then you have the same thing. Or you can think about, you can have something like asymptomatic infection or carrier states, and earlier we talked about a latent state in TB, so you could have something which you can enter and you can leave it again, or you can have asymptomatic infections, so you could have people who become infected and then perhaps after a while become symptomatic and these kind of things. So you can put this into the compartmental models. And I said that we didn't have any disease-related mortality. So in that model that I showed you, everybody had the same death rate, but if you have an infection that kills, of course, then the death rate of infected people would be different from the death rate of susceptible or recovered people. And you can have heterogeneity in terms of things like age. For example, you can look at different age groups and how they become infected. You can also have different risk groups, so perhaps people in certain there could be social risk groups, or there could be risk groups in certain area. I talked earlier about hotspots, or there could be a behavioral risk group. So there's all kinds of things that you can put into a model. And the problem is there's always things that you can do to make your models more realistic and more complex, but then you also need to have the data to inform them. So for example, if you make a model of age-specific infection, you have to know how susceptibility changes by age, or how infectiousness changes by age. And often you also have to know what are the infection rates of age groups to each other. So for example, you can have an age-based model where you have school children, but then you need to know how much more infectious school children or how much less infectious school children are to each other than they are to adults or adults with each other. So it always comes back to having the right kind of data. And if you don't have any good data, often or usually you're best off using a simple model, because otherwise you are just speculating with a complex model. You might have tried to make your model very realistic, but if you can't inform it, then you're better off with a simple model. And if your simple model doesn't describe the data well, maybe then you need to think about getting more data, and perhaps your model can recommend or can make suggestions for the kind of data you would need. And I mentioned earlier these three purposes of using models: that you want to understand transmission dynamics, you want to assess control strategies, and you want to perhaps predict the future course. And you can make very powerful predictions with models, and many predictions that have been made have been confirmed. And we've had a bit of a look of how you can build these simple models to describe a spread of an infection in a population. And what we often do with models is that we investigate things like vaccination or control strategies. So just to remind you of these things and link them to what you have seen in the last 1.5 hours or so. I don't know if this is the lights seem to have gone off. I don't know if this is my signal that it's time to end. So I'll end on saying that when you build a model, it's important to always challenge the model and always challenge it. Always think about whether you have the right level of realism. And I think that's really the key intellectual challenge in modeling in general, is to have an awareness of how simple or complex your model must be. And there's no general right or wrong answer, and it's just important to keep an awareness of it and to bear this in mind when modeling. Think about what the assumptions are, whether they are reasonable, how one could improve the model, and whether the right data are available. Okay. So just to briefly remind you of all the things that we've gone through in this lecture. So we've talked about, initially, we've talked about R0 and the reproduction number, about the standing epidemic. And we said that we have the mathematical model as a mathematical description of the dynamical process that we said we want to describe how something changes over time in a population. And we saw that we can do this with compartmental models that have state variables, so this S, I, and R, and then some parameters. And we saw the two basic compartmental models, the SI model and the SIR model, which we then simulated, and we saw how we could link the SIR model to the earlier concept of the basic reproduction number R0 and the net reproduction number that will tell you whether something spreads or dies out, or whether infection at any time increases or decreases. And we also saw that we can use this to determine the proportion of a population that needs to be vaccinated by means of the herd immunity threshold. And then in the second part, we talked about endemic diseases, And we said that the SI and the SIR model cannot be used to describe endemic diseases because there are no new susceptibles that come into the population. And we talked about two simple ways of introducing new susceptibles in a population, one being the SIRS model, where there's loss of immunity, and the second one being an SIR model with vital dynamics with birth and death, where new susceptibles are created by birth. And we saw that we can get cycles from the SIR model with birth, and that alone, however, is not enough to produce a really regular seasonal pattern, that you need some other seasonal variation, whether it's a climatic or some environmental seasonal variation or something like the school year. Right. Are there any remaining questions about this? Yeah.
Hello. If we say vector-borne disease, how we can include like seasonal parameters?
Okay, so for a vector-borne disease, you would, if you wanted to introduce a seasonal parameter, you would, instead of having the beta, which is the infection rate, you would have a beta which itself changes over time. So you have a beta which goes down, say down in the dry season, and up in the rainy season. So you would need to have some idea of how the so it comes a bit back to what I said earlier. You have either that, the beta, or you have a mosquito population where there are births and deaths, and the birth rate increases in the rainy season. If you know, you would have to have some kind of idea of how the seasonal variation in the weather patterns affects the birth rate of mosquitoes.
What the cycles signifies in SIR models? Cycles.
Say again, sorry?
Cycles, what they are signifying in SIR model?
What do the cycles signify in the SIR? So what we mean by cycles is this this. So that you can have something that appears regularly every 2 years or so, or every year if you have an outbreak or something. That's what we call a cycle. And so in the SIR model, you get this with something where you can put it, if you put in births or deaths, for example.
And another question, how we can, is there anything, any tool so that we can, there is no cycle, means we will not get cycle. Is there any tool for that?
So you mean how do we know whether there's cycles or not? Or?
Yeah. Means how we can, means if cycle is there, then how we can, can we implement something that cycle is not there? Cycles, we will not get cycle.
So is the question how do we control a disease?
Yeah, how
cycle?
to control these cycles, yeah.
Or how do we introduce cycles in the model?
No, how to control cycles if cycle is there.
Okay, what do we do? Okay, well, I mean, so it depends on the disease really, but what the cycles allow you to do is they allow you to sort of predict when you would expect another outbreak. So it would allow you to somehow increase your efforts. If you know that something comes every 3 years or so, then you would. But what exactly you would do would depend on the disease. I mean, with measles, for example, so we have a vaccine, so we vaccinate, and there's no particular response that we need to do. But for something, I don't know, for example, if you had a vector-borne disease that has an outbreak every number of years, and we know what the cycle is, then perhaps there's a way in which we can affect this, or we can concentrate our efforts. I mean, the other thing is, apart from cycles, is that this kind of theory has been used to predict when you would expect an outbreak, for example, in populations where there's vaccination against measles, but not enough vaccination. So if there's some kind of, we've seen that the herd immunity threshold for measles is quite high, and there was a famous study in New Zealand in the late 90s where they said where it was clear that not enough people were vaccinated, and so you can work out, by taking the birth rate and the vaccination rate, you can work out how long it will take until your net reproduction number will cross 1, and you will be in a situation where you can get an outbreak. So you can sort of make a prediction on that, and so you can tell, for example, how much time you have to catch up and to try to vaccinate those that are not vaccinated before you would expect a big outbreak.
And treatment also. vaccination and treatment also is a control measure, I think, for that.
Yeah, I guess, yeah.
Yeah.
It's not necessarily for in measles, but yeah, depending on your disease, it would be
depending on the
vaccination
disease, yeah.
or treatment or prophylaxis or whatever is the appropriate measure. Yeah.
Okay, thank you so much.
Okay. Yeah. Okay, so can you say again with the microphone? Sorry.
Shouldn't we have a different death rate for the infected people?
Well, yes. If the infection kills, then yes. So what you can do is, here in this model, well, let's just go back to the model picture, this one. So what you can do is you could have, so this mu is the kind of the general background, what we call the background death rate. So this is the normal death rate in the population. If your infection kills, then you would have another arrow here from I down, which is the disease-related mortality rate, which will be much higher usually than the general mortality rate, because if the disease kills, then you would have a high rate going from here to here. Yeah, that's right. So. Say again, sorry?
As long as your immune system is compromised, like you should have a higher death rate.
You should, yeah, say again? You should have a higher death rate.
It's on,
yeah.
okay. So even if the disease may not be fatal, but the point is if your immune system is compromised with the infection, then you should essentially have a higher death rate for that case, isn't it?
Because of everything else that's
going on. There is no infection, I guess, which doesn't compromise your immune system. Like you're as good as any one person, just infected. That's a very benevolent infection, I suppose.
Yes. Okay. So well, I mean, I think.
That's the commonest one.
How is it?
What you are thinking is the commonest one.
Okay.
I'll talk about it.
Oh, cool.
Great.
Fine.
We'll hear about this afternoon. Yeah, but I mean, this could have the same effect. I mean, if your disease doesn't kill you directly, but compromise your immune system, again, you could have a different mu here for the infected people than for the others. Yeah, you would have two different death rates: one for susceptible and recovered, and then one for infectious people.
There are several risk factors contributing susceptible to infection. How can we consider those?
Say again, sorry.
Several comorbidities contributing to the susceptible to infection compartment.
The what from susceptible to? Yeah, thanks.
Several comorbidities, risk factors like for TB, for HIV we have TB. Several comorbidity factors influencing S to I.
Okay.
So how are we going to account those things?
So what kind of factors? So you mean like HIV, like co-infection, or
S co-infection or the BMI factors?
Yeah.
Or several.
Well, okay. So I mean, so co-infection. So if you wanted to look at co-infection, you could have a model where you could have two different SIR models that describe the same population, and then being infected with one perhaps changes your beta of being infected with the other. That would be looking at co-infection. If you want to look at more generally, if you know about risk factors or something like this, then you would split up your population into, for example, different age groups or risk groups or something. So you would have an SIR for.
So I need to have a different S, or.
Yeah, you could have different S exactly, and people are by some means or the other are in one S group or another S group, and then they go into different I groups, and then what changes is the force of infection. So, for example, you could have instead of having, let's look at this. Actually, no. Well, instead of having, that's not a good one to show. Here, instead of having beta times I over n, you could have beta high risk times I high risk plus beta low risk times I low risk. So you could have different infection rates from different population groups, and you can also have different infection rates depending on which risk group or something you are in. Yeah. So you would have different values for the beta depending on some kind of risk factor or comorbidity or whatever it is. That's what it would always come down to. Okay. Any other questions?
Okay. How do you establish the model for a pathogen which is having antigenic plurality?
Where are we?
How do you establish the model
for a
pathogen which is having antigenic plurality without cross protection?
How do we establish what? Sorry.
Pathogen which is having antigenic plurality, like FMD, influenza.
Yeah. What about them? Sorry. How do you establish with FMD and influenza? I didn't get the middle of it.
Antigenic plurality. So it's different kind of strains.
Okay. Different kind of strains. Well, actually, in the same way as this. I mean, okay. So it's people have looked at this a bit. For example, for influenza, and you can. There's a way. Yeah, you can have. So if you can treat them just as different infections, and then you're back to the model that I described earlier, where you have comorbidity or something. So, but I mean, you can have. So, for example, you can give going back to the picture. Let's say. So we can give everyone here an index. Say I1, for example, and I1 or I2 or I3, which means being infected with strain 1, strain 2, or strain 3. Okay, and then perhaps being recovered from the strain 1. So you become susceptible. If you get infected with strain 1, you become I1. Then you recover, flu or something, you become an R1. And perhaps being R1 reduces your susceptibility to strain 2. Okay, so then if you're in R2, maybe you can still become infected with strain, so you become an I, or if you're in R1, you can become an I2, but with a lower infection rate, maybe, or something like this. Or maybe you can have. And then if you have both, if you've had both, you become an R1, 2, and you cannot be infected with anything anymore. So you can, just by dividing the population up, you can look at things like different strains or something. So you would treat them like different infections, and then you can think of things like cross immunity or something like this. Okay. Any other questions? I don't know. Is there a program point at 11:30? Should I? Coffee at 11:30. There's coffee at 11:30. All right. Any more questions, or would people like coffee? All right, let's have coffee there. Thanks.
There's coffee outside. Join us.
You can ask me over coffee if you have further questions.